that we're going to look at today that will be on the exam is what we call line structures. Then we'll talk about alkenes and alkynes and structures of double bonds and triple bonds. And that's it. So let's look at line structures. I just want to warn you a little bit about the language, not the profanity type language, but I call these things line structures. Some books call them, most books call them line structures or bond line structures or something like that. Our book uses a different term, which is skeletal formulas. So those are interchangeable. I will talk about them as line structures, but you'll see them in the book as skeletal formulas, and you may see either one on the exams, depending on who's writing the questions. So here's what they look like. I think it's easiest to start with just a visual example. If we take hexane, we know this is the condensed structure, 6 carbons in a row with the proper number of hydrogens as well. And the line structure looks like this. So different, I guess, is pretty clear. One thing that you can notice as you're copying this down is that the line structure is a whole lot faster to write, a whole lot easier to write. But because it's a type of abbreviation, we throw out a lot of information when we go from the condensed structure to the line structure. So in order for that shorthand to be effective, we have to know what we're talking about. We have to know what that thing means, that little zigzag line means. So can anybody, just looking at those two structures and comparing them, what do you see that could show how they're the same? What do they seem to have that's similar?
The same number of changes in direction / endpoints. Yeah,
if we think about the ends and the little points of these zigzags, you can count 6. So 1, 2, 3, 4, 5, 6. And similarly, in our condensed structure, we see 6 carbons. So we might say something about that connection. And that is indeed our first rule of drawing line structures. We can call these rules or assumptions. And first, we're going to assume there is a carbon at each end and vertex, which is another way of saying intersection. So anytime we have an end of a line, or we have a place where lines connect or intersect, we're going to call that a carbon. So if I have some kind of a shape like that, how many carbons are represented there? 4. Does everybody see 4? Anybody not see one? Let's circle them. 1, 2, 3, 4. 4 carbons represented in that shape. What about this? Now that's a square, obviously, or a rectangle or whatever. But if we think of it as a line structure, what does it tell us about how many carbons are there? Using those rules.
There's 4.
Still 4, right? Each corner of the square is an intersection, can be thought of as an intersection of 2 lines. So those are going to be our carbons. So a line structure is just made of lines, but based on how they intersect and where they end, we can figure out where the carbon atoms are. Now, one consequence of that is that when we draw this, we have to use that zigzag. Because if you just drew a straight line, you wouldn't know where the different endpoints were. So we use this up-down motion. And coincidentally, or not really, because that's how it was designed, this is the shape, the proper shape of the molecules anyway. Remember when we looked at those 3D structures, we saw that the carbons kind of went like this in that structure. All right, so that's our first rule. So what's missing from the line structure? Hydrogens, and we don't draw the carbons. So we also have to think about how many hydrogens are there. If the hydrogens aren't shown, how can we figure out how many are there? If we're not going to put them in explicitly, there must be a way to figure them out, otherwise it's not a very good abbreviation. So how do we figure out how many hydrogens are supposed to be on each carbon in a skeletal or line structure? Yes?
3 carbons, 4 bonds.
Well, yeah, so for each carbon, we know we need 4 bonds. So we have to assume there's enough hydrogens on each carbon to get to 4 total bonds. That's our second assumption. Assume there are enough hydrogens so that each carbon has 4 bonds. All right, so let's look at an example here. So let's look at this structure. There's a line structure, and we can pick out the carbons based on where the lines end and where they intersect. So let's look at how many hydrogens would be on each carbon. If we look at this first carbon on the end, we can see that that carbon has 1 bond to the carbon next to it. You see that? 1 bond to the carbon next to it. So that means how many other bonds or how many hydrogens have to be on that first carbon to have 4 total bonds? If we want a total of 4, how many more hydrogens do we have to add there? We need 3 more hydrogens. Can you see that? We want 4 total bonds, so we go 1, 2, 3 more hydrogens, and that gives us 4 total bonds to that carbon. So then how many hydrogens need to be on the next one? 2, yeah. We've got 2 bonds already to the 2 carbons, so 2 more hydrogens. This one needs 1 then, and these are also CH3s. Whoops, not CH. So you can figure out how many hydrogens need to be on each carbon based on how many bonds are shown or not, and then how many more it needs to get up to 4. What if a structure like this? This one has a double bond. We'll get into this, called an alkene. We'll get into that later in class. How many hydrogens, or here's a question I might ask. Like on the exam, what's the formula of that molecule? So see if you can figure out how many carbons and how many hydrogens should be in that molecule. It's carbons based on the intersections and the ends of the lines, and then hydrogens based on making sure you have 4 total bonds. I count that out and write it down, because then when I show you the numbers, I want you to critique what you wrote and see if we'll see if you were right or not, but if you weren't, where were you off and where were you counting or not counting? Got some numbers? Got some counts? All right. So I count here 4 carbons. Got 4 carbons? Do we get more than 4 carbons? Less than 4 carbons? Nobody wants to say?
I thought
Yeah.
we had to put one at the bottom one where you just put the C. I thought it had to be like a C on each line going down.
Oh, so the double bond would have 2 C's? Yeah, that's a possibility. But in this case, we have a double bond going between 2 carbons. We haven't really seen those yet, so that's a totally reasonable way to have written that. But so now you know that just means there's 1 carbon there. If those lines were kind of spread out more, then we'd call it 2 different carbons. Okay, so let's count up the hydrogens then. Each carbon needs 4 bonds. That means we need 3 over here. We need 3 over here. How about in that middle one? Doesn't get any hydrogens. See that? It's already got 4 bonds. 2 from the double bond and then 2 to the other carbons. And then on the bottom, we'd have 2 hydrogens because it already has 2 bonds going up between the 2 carbons. So that's 4 total. So that means that the formula of this compound should be C4H8. All right. And our final rule of writing the line structures is that all non-carbon, non-hydrogen atoms do not get changed and their hydrogens are still shown. So what that looks like is, let's say we have a condensed structure that looks like this. We'll get into this in the next chapter, but that thing coming off of that 3rd carbon in there is an OH. It's called an alcohol group. It's an oxygen with a hydrogen on it. So when we're thinking about how to build a line structure, first thing you do is you figure out what the longest chain is, just like when you're naming, so that you can draw a line structure of that longest chain. In this case, it's 4 carbons. So we're going to draw 4, 1, 2, 3, 4, like that to make our line structure. So that's always the first step. Draw your longest chain because you can just zigzag however many carbons you want. After you do that, go back and recheck how many you actually drew. So 1, 2, 3, 4. The reason for that is because of the way we draw it. A lot of times we forget to count that first point when we're drawing our chain. So instead of going 1, 2, 3, 4, we go 1, 2, 3, 4, and that actually ends up with a 5 carbon chain. So make sure you always go back and check it that you have the right number. All right, so if we're trying to make this same structure, on the 3rd one from the left, we should draw the OH going down. And because of that rule, we leave that thing alone. So the end of that line does not represent a carbon because there's an O right there. That represents that OH coming down, and we don't leave the H off. The reason for that is that other atoms don't have that same rule like carbon does. So carbon, we can say it's always going to have 4 bonds, and we always know how many hydrogens are supposed to be on it. Other atoms, we don't. So we have to explicitly say how many hydrogens are on other types of atoms. Only the hydrogens on carbon atoms get knocked off in the course of drawing these structures. All right. So one thing you should be able to do, or well, that we'll work on until you can ultimately do it, is drawing some structures from the names. So I'm going to write down 2 names, and I want you to try to draw line structures of those compounds that we're describing here. So first one is 3,4 dimethylhexane, and the other one is 3-chloro 2-methylhexane. Let's see if we can draw structures for those 2 molecules.
The skeletal structure.
Yep, the skeletal structures. And that's actually, if you have trouble going directly to the skeletal structures, that's fine. Draw a condensed structure first, and then convert it, and then it might be easier for you to convert it into the skeletal structure. Let me know if you're really stuck. Get started. How many carbons are in hexane? 6, yeah. Those are both going to be based on 6 carbon chains.
You said 6 carbon in your own. Actually, it's been 6 carbon. Yeah, so you branch out from 2 and 4. So you still have 2 like that. change it to 6. We go 1, 2, 3, 4, 5, 6, and then jump 2, 4. Oh yeah, so the name isn't the total number of hydrogens. So it's like just the main chain. The other ones are extra. Yeah.
Okay, in this first one, let's quick review how to write this as a condensed structure, and then we'll turn it into the line structure. And the second one, we'll try to just write as a line structure. So as a condensed structure, the first thing you look for is that main part of that name, which is, in this case, is going to be hexane. That tells us there's going to be 6 carbons in a row. You can draw that row however you like, straight across, up and down, whatever. But that's 6 carbons in a row. So C, 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 C. I like to draw them without the hydrogens first because depending on what's connected, we may have to change our hydrogen count a little bit. All right, so then we've got 3,4-dimethyl. So I can number these. And off of number 3 and number 4, I'm going to put methyl groups, which are single carbon groups. Now we can fill in the rest of the hydrogens. Anything that just has 1 bond gets 3. Anything that has 2 bonds gets 2. And anything with three bonds already gets 1 more for hydrogen. So that would be our condensed structure for 3,4-dimethylhexane. Then here's how we turn that into one of these line or skeletal structures. We start the same way. We'd say we need a 6-carbon chain. So we go 1, 2, 3, 4, 5, 6. And you can start going up or you can start going down, doesn't matter, as long as you somehow zigzag that to get 6 carbons. We check it, and this time we can just check it with numbers because we need those numbers anyway. 1, 2, 3, 4, 5, 6. Oh, great, we made a 6-carbon chain. Okay, our methyl groups then are going to go on number 3 and number 4. Now, which direction do you have them go? The convention here is that you want to keep those bond angles as wide as possible to most approximate what the actual structure would look like. So that means when we look at carbon number 3, we want to make that methyl group come down like that so that we have that nice wide angles. If we made it going up, it would kind of cross right in between those other two. And that's not really what that structure would look like. It wouldn't be that close together. So then when we move over to number 4, we would connect that methyl group up like that to, again, preserve those bond angles. Connectivity-wise, it doesn't really matter. Connections are connections. But the convention is to do it this way because it makes it look a little bit nicer. So that's what you'll see. Because methyl groups are just a single carbon, we leave that line empty at the end. And we know that that end means that there's a carbon there with 3 hydrogens on it. That's our abbreviation from the line structures.
If it was an methyl group, would
Yeah.
you just draw it like for the 3 straight down and then just
Yeah,
writing
so straight down and then like another thing coming off that way. Yep. All right, for the next one, let's see if we can do it just from drawing the line structure. So hexane tells us we've got a 6-carbon chain. 1, 2, 3, 4, 5, 6 carbons. We're going to check that again. Okay, got it. Got all 6. Didn't put 7 by accident. And now the name is telling us that we need a chloro on 3, which is chlorine, and a methyl on 2. So we can add those. 3 gets a chloro. And we don't abbreviate that because it's not carbon or hydrogen, so we put Cl. And then number 2 gets a methyl, and we leave that one just like that. And that's our structure. So in one way, these structures are easier to draw from the names than the condensed ones because you don't have to worry about how many hydrogens are on each carbon. You just assume how they are, whatever. So whenever you draw more lines, you're cutting down the hydrogens, and you don't have to do anything about it. It just happens. Over here, when we make branches off of the chain, we have to have fewer hydrogens on that carbon to account for it. But this is just the kind of thing that takes practice. So go through your practice problems. I can get you more if you need as you do your studying this weekend. And as you practice this and get a little bit more comfortable going back and forth between these types of structures, it'll work out, I think. We'll do some more today too. So we're going to practice this in a couple different ways. All right. Let's look at how naming works when we're dealing with line structures, or especially these kind of hybrid line structures that you see sometimes. Oops. It's a little bit bigger. Let's look at a structure like this. This is a little weird because it's basically a line structure, a skeletal structure, but then also CH2, CH3 is drawn on that side. And that's somewhat common. It's probably a little bit more common to see it like this. It's kind of like all the ends get capped off, but the inside of the structure still looks like a line structure. So that's something you see sometimes. And we have to use our understanding of both styles of writing structures to understand what's happening here. So how would we name this structure?
By the longest chain.
By the longest chain, yeah. So what's the longest chain here?
7.
7? Where do you see 7?
Starting at the top left, the CH3, and then kind of looping around to the ethyl group.
Yeah, so all of these carbons are connected in one 7-carbon chain if you step from one to the other. So you got to be careful with stuff like that because it's easy to get distracted and just try to pick the horizontal one, the one that's going across here, which is 5 carbons. So make sure you really look for all the connections to try to see if you take some turns and you can get an even longer chain. Okay, so that's 7 carbons. And we can number those 1, 2, 3, 4, 5, 6, and 7, connected one after the other. A 7-carbon chain is heptane. And then we name the substituents. We have methyl groups on 3, 4, and 5. So that name becomes 3, 4, 5. Trimethylheptane. Remember, this exam is really only on 3 chapters. Chapter 10, acids and bases, chapter 5, nuclear chemistry, and chapter 11, this stuff. So this kind of thing is going to be a big part of that test. So make sure you get a lot of practice and you feel comfortable with it before Tuesday. Okay. The next part we're going to look at, and then we'll keep practicing this all together, is the alkenes. Which are double bonds, and alkynes, which are the triple bonds. So now we're talking about multiple pairs of electrons shared between carbons. And the way these look in line structures is very similar. So if we had something like this, the line structure would be 3 carbons, and then we'd show a double bond between the first 2, like that. Just 2 lines right next to each other tells you it's a double bond. If you had a triple bond, it looks a little bit different because triple bonds can't bend. So our line structure ends up being like this. You can see where the carbons start, 1, 2, 3, because of the break between the triple bond and the single bond, but they stay linear. They don't bend the way that the double bonds do. Okay, let's look at the name of these. First one, the double bond, is called propene, and the triple bond is called propyne. So hopefully you can see that this is just an extension of what we've already been talking about. The difference now is that because it's a double bond, we end the name in "ene" instead of "ane," or if it's a triple bond, we end in "ine" instead of "ane." So just to change by 1 letter when we talk about these names. Now there are a couple more consequences on naming from dealing with double bonds and triple bonds. One, sometimes we need to specify where the double or triple bond is in the chain. So let's take a look at some hexanes. Oops. So think about those 3 molecules. Those are different because the double bond is in a different place. Those are isomers. They have the same formula, but the double bond is in a different place in each one. So they need different names. But so far, based on what we've done, those would all be called hexene because they have a double bond. So it'd be hexene, hexene, hexene. That's not good enough because those are clearly different. So the way we differentiate them is to put a number in front of the word hexene, indicating where that double bond starts. This one starts at carbon number 1. So we call this 1-hexene, or hex 1-ene. Either is correct. Usually for simpler structures, the first version is used, and for more complicated structures, the last version is used, but it doesn't matter. The next one then would be 2-hexene, because the double bond starts at carbon number 2. And then what about the last one? 3. Everybody see that? The double bond starts at number 3. So this one's 3-hexene. So that's one issue that comes up with double bonds. We need to specify where it is in the chain, so we put this number. With propene, we didn't do that because there's only one possibility. Even if the double bond were on the other way, going the other way, we would just start counting from right to left instead of left to right, and it would still be 1 propene. So if there's no possibility of difference, then we can leave the number out entirely. But if there is a possibility of different alkenes, we put the number in. And if you're ever not sure, put the number in. It's never wrong to put the number in. to the name. Okay. Another aspect of double bonds that's a little bit different is that double bonds can't rotate. If we look at butane, just regular old butane, one of the things we did the first time we were drawing structures and things is we were trying to figure out which structures were isomers or which were the same. Remember doing that? We drew them on the board and kind of had them all going in different directions. And the reason we could do that is because no matter how you draw 4 carbons connected in a row, these are exactly the same. They're equivalent structures because single bonds can twist and do whatever you want with them. So it doesn't matter how you draw it, it's always the same. With double bonds, that's not the case. And I'm going to go back to our condensed structure so we can see it a little bit more clearly. And then I'll draw the line structures as well. These two structures are not the same. So let me draw them in line structures so you can see that as well. It's very similar to what we just saw with butane, but because of that double bond in the middle, those are no longer the same. They have the same connectivity. They're both 2-butene because the double bond starts at carbon number 2. But because they can't rotate, those aren't the same. And so what we do to figure this out is we have to give them another name or use some other indicator to show that these are in fact different structures. So what you do is you draw a line or a pretend line parallel to the double bond, like that. And then you look and you say, are the major groups here on the same side of that line or on the opposite side of that line? So what would you say for those two? What's the first one? We're going to call the first one opposite, right? You see those two, either you look at the hydrogens or you look at the methyl groups. Either way, they're on opposite sides of that line. And then the second example, they're on the same side of the line. Everybody see that? So the way we differentiate those, because these are both types of 2-butene, the way we differentiate them, since they are actually different structures, is we call this one trans 2-butene, and we call this one cis 2-butene. So trans means opposite, cis means same. So if they're on opposite sides of that line, we call it the trans isomer, and if they're on the same side, we call it the cis isomer. And that doesn't happen with single bonds. Actually, it doesn't happen with triple bonds either because they're straight. Only happens with double bonds. So if you want to look at a double bond and try to decide if it's in the trans or the cis orientation, you draw a dotted line through the double bond, and you try to determine whether those major groups are on one side or are on the same side or opposite sides of that line. Then the last thing that's different about double bonds with respect to naming is that double and triple bonds should be numbered as part of the longest chain and given the lowest possible number. The reason for this is that we mentioned this a little bit. Alkanes don't really do much chemically. They burn. They can do a couple other little reactions, but they don't do a whole lot. Alkenes, double bonds, and alkynes, triple bonds, do a whole lot. They do all the actual chemistry. They do the reactivity. So when a molecule has a double or a triple bond in it, that's the most important part of that molecule, assuming there's nothing else in there, which we'll get to in the next chapter. But if it's double bond or triple bond, that's an important part of the molecule. So the name has to reflect that this is a molecule with a double bond in it. So let me show you what I mean. That's getting weird all of a sudden. Okay, let's take a look at this structure. So normally when we do our naming, we'd say the longest chain is what? 7 straight across from left to right. Everybody see that? Or right to left? Because there's a double bond there, we can't pick that as our main chain because then the double bond is coming off of the main chain instead of a part of it. So instead, we should pick our main chain like this, that includes the double bond. That's the correct longest chain for this molecule. That horizontal one that doesn't have the double bond in it is not the main chain. We should number it so that the double bond has the lowest possible number. We can't put a 1 on the double bond because it's in the middle of the chain. But if we start numbering from that little thing that's sticking up at the top, we can go 1, 2, 3, 4, 5, 6. And so this molecule would be named as a 2-hexene because it's got 6 carbons and the double bond starts on carbon number 2. And then the substituent is that other thing hanging off, which has 3 carbons. So that's 3-propyl 2-hexene. You see how that works? We have to include the double bond in the part of the main chain. Another time this can get a little bit tricky is when we are in a ring. Let's say we have this structure. We talked about cycloalkanes last time. We can have cycloalkenes too. In this case, the double bond is inside the ring. So we already know we're going to use that ring as our main structure. This is going to be called a cyclohexene. But the question is, where do we start numbering? Because in a ring, you can start wherever you want. And the rule from last time was that you start wherever it gives you the lowest substituent numbers. So like, if we're doing that, we would start at where one of the methyl groups are and call it 1,4-dimethyl as we count around the ring. But because of this new double bond rule, we can't quite do that. So we want to start the numbering at one of the double bonds. And if we do that, that means our numbering has to go from 1 to 2 along the double bond. That looks like this. 1, 2, 3, 4, 5, 6. So now that name becomes 3, 6, dimethyl 1-cyclohexene. Okay, we've got to remember to get that cyclo in there because it's connected around in a circle or in a ring instead of just a long chain. And we need to watch our counting because 1 and 2 have to be the double bond. Now that 1 in the name, we didn't have to put that there because in a ring, there's only one type of cyclohexene, but it's okay, we'll leave it in there just for consistency. All right, how do you feel about that so far? Can I take a little practice? Will work? Yeah. All right, so for an exercise, what I want you to do now is I want you to draw a structure. The structure should have a double bond in it somewhere and some stuff coming off of some stuff. But other than that, it's up to you. You can draw rings, you can draw chains, you can draw whatever. I want you to draw some kind of a structure with a double bond in it. And then when you've got it, I want you to try to name it, but don't worry if you can't. And I want you to draw the structure up on the board without the name. And we're going to look at it and try to see if we can name it, and we'll all write these structures down and help, and that'll be part of our practice. And maybe if there's some good ones, I'll put them on the exam. So see if you can draw a structure that includes at least one double or triple bond, and post it up on the board, even if you aren't sure how to name it. You can put halogens on there, FCl, BRI. Stay away from like oxygen and stuff because we haven't talked about how to name those yet. Other than that, whatever you want to draw, and go ahead and put it up on the board. As they go up, I'll post them on here. Oh, we have more markers. There's lots more markers up here. Grab some. You can draw up here, you can take markers back over there. Anybody else see a marker? But you gotta have some more structures. Well, people here. Need more practice. They don't have to be like anything in particular, just whatever you can draw. Go ahead and draw it. Thanks. All right, so we got 5 structures. There's 11 people here. 3 of the structures are drawn by the same person. So come on, let's draw some more structures. Thank you. Thank you. What else we got? Do you have a structure for us? You want to draw a structure?
Oh, yeah.
Thanks. No one else wants to, so we only have a couple. Thanks. That's all right. We got a good mix now. So. Great, thank you. All right, this is a good mix. So, you can name these? Maybe? Are there any that you look at and you think, like, I don't even know where to start with that one? Any of these seem especially unusual to anybody?
That one has 5 bonds.
Oh yeah, okay, so this one down here, we got an issue where this carbon has 5 bonds, 1, 2, 3, 4, 5.
Oh, yeah.
So-
I have it written down differently here. I wrote it down wrong.
Can we do like that?
Yeah, I did one on the other bond.
Oh, over
On the
here?
top, no, the other one.
Over here? Over here?
Yeah, does that work? If there's
Like
not-
going up like that?
Yeah.
That?
Yeah.
Yep, that works. That works. There's still a weird thing about this one though that we haven't really talked about, and that's that it has 2 double bonds. So what do you do if something has 2 double bonds? Let's look at that one together, and then I think you can probably do the rest of these. So if there's 2 double bonds, we're going to pick our longest chain with those double bonds in it, assuming that works. Like that. That's going to be our longest chain. And then we want those double bonds to have the lowest possible numbers on the chain. So we number 1, 2, 3, 4, 5, and 6. So normally this would be hexene, 6 carbons, but we've got 2 double bonds in this case. So instead of hexene, this one's going to be hexa 1,3-diene, to show that there are 2 enes on 1 and 3. Now, this is not something that's in the book. This is not something that will be on the exam, but that's how you deal with it when there's 2 double bonds. The rest of it are the 3 methyl groups on 2, 4, and 5. So I'm not gonna have enough time or room here, but 2, 4, 5, trimethyl hexa 1,3-diene would be the full name of that molecule. Okay. The other one that's a little different, well, not a little different, but that we haven't done an example of is this one here with the triple bond. How would we name that one? Yeah.
Is it 1,6-dimethyl hexane?
Close. So in this case, you're right with the hexine part. There's no substituents because all the carbons are part of that chain. So we would number the chain as 1, 2, 3, 4, 5, 6, like that. And that would make this 2-hexine. That main chain word, whether it's hexine or hexene or whatever it is, that doesn't include that doesn't include the substituents, but it does include everything in the chain. So if you're including everything in the chain, you can't also have, or if everything in your molecule is a part of that chain, that means there's not going to be any substituents out in front because there's nothing hanging off the chain. Okay, the other ones all pretty much follow the rules as they should. So see if you can come up with some names for these remaining 5 in the next 5 minutes or so, and then we'll go through it. How's it going? Got some names? All right, take like one more minute and then we'll go through it. All right, let's take a look at these names. So the first one, I see the longest chain going straight across the middle. So we're going to, it doesn't really matter where we start here. We'll start over here so that the ethyl group gets the lower number. 8 carbons is octane, and there's a 4-5 double bond between 4 and 5. So that gives us 4 octene. The substituents are 3 ethyl and 6 methyl. Oh, ran out of room. It's 3 ethyl, 6 methyl, 4 octene.
Do you have to write the 4 since it's like right in the middle?
Yeah,
You do.
because there could also be a 3 octene or a 2 octene or a 1 octene, which would be different depending on where that double bond is. This particular double bond, is this a trans double bond or a cis double bond? Yeah, this one's trans. If you make that same kind of dotted line that goes parallel like that, you can see that the main parts of the chain are on opposite sides of that line. Another way to look at it is the trans double bonds are the ones that kind of follow the shape of the line, like the zigzag thing. And a cis double bond makes it kind of kink around like that. Okay. Next one, and stop me if you have questions. 1, 2, 3, 4, 5. So that would be 3, 4, dimethyl 1, pentene. This one's just one pentene. This one over here, we got to start numbering right like this because we want the double bond to be 1 and 2, and then we want the methyl group, the substituent, to be number 3. So that's the best way to start numbering that, and that gives us 3 methyl 1 cyclobutene. And then finally, this one, 1, 2, 3, 4, 5, 6, gives us 5-chloro 3-methyl cyclohexene. Questions on any of those?
For the one you just did,
Mhm.
before the cycle, we don't put the 1 for the.
Oh yeah, you can.
But
In the rings, we usually don't because you can start counting wherever you want. So you usually always start right at the double bond, which makes it 1. But it's not wrong to have the 1 in there. Thanks. Other questions about those? Okay, I'll see you upstairs in about 15 minutes.